Bismillahirrahmanirrahim. My dear students, the topic domain decomposition method was our last topic, and then after the university was closed due to the pandemic situation, and I'm hope that you all are fine at your home and you are safe at your home. The book which we are using to discuss this domain decomposition method is the partial differential equations and solitary waves theory by Abdul Majid was, and this book was published by the Higher Education Press, Springer, and this book is freely available on Google. So you can Google this book and you can download this book freely from Google. So this method was introduced by George Domian in 1984, and this method has been receiving much attention in recent years in applied mathematics in general and in the area of series solution in particular. The method, this method proved to be powerful, effective, and can easily handle a wide class of linear or nonlinear ordinary or partial differential equations and linear and nonlinear integral equations. This method has fast convergence, and this method can be used to solve the nonlinear ODEs, which is occurring in the physical phenomena of fluid dynamics, and all mathematical shapes of the physical structure in fluid dynamics can be solved by using this domain decomposition method. The general form of the domain decomposition method is, for example, let's say we have an unknown function u is an unknown function, and once we decomposed this unknown function in a series form where this unknown function is equal to summation n from 0 to infinity un, and un is depending on the independent variable x and y, and further this function can be written, if you open this summation, this can be written u naught xy, where xy are the independent variables, plus u2 uh, u2xy. It's a bit difficult to write mathematics, but we are trying our best. u3, uh, this is u2 xy depending on xy, and this is u1, this is u1 basically, plus up to so on. The last term is, suppose we are taking un, and this un is again depending on the independent variable x and y. For instance, you can consider this un as a velocity field of any fluid phenomena. So this is basically the unknown function for in the differential equations. So this unknown function can be decomposed in a series form, and in this slide this is exactly the general form of any differential or ordinary differential or partial differential equation, where L is the linear operator, u is the unknown function which is depending on xy, r is the remainder term of u, and g is the source term, which is in this case is a constant value in a differential equation. So what exactly this L is in this general form? This L is the higher derivative, which is assumed to be invertible in this case. For example, if we are dealing the second order differential equation, so in second differential equation, this L is equal to d square u or d square by dy square or dx square. So for second order differential equations, this L is equal to d square by dy square, and this is invertible. By invertible we mean that the integration of this L is exact, or L inverse is equal to which is invertible is equal to the two time integration of the function unknown function u x, and यहाँ पे if you look at this one, जो independent variable यहाँ पे use हो रहा है, that is exactly y. So since we have two time integration, so this will be dy into dy. So this is now the invertible form of this linear operator, and r is uh, the term in the differential equation which has less degree uh, than the linear operator, and g is the source term in this equation. So this is the general form of any ordinary differential equations or partial differential equations. Now, how to solve this general form by using the domain decomposition method? This is exactly the question. This is exactly the goal, that how we can solve this general form by using this Edomian decomposition method, which was proposed by George Edomian in 1884. So to answer this question, we need to apply the invertible operator on the general form of the equation. So once we apply the invertible operator, this was exactly the previous form of this general form. Lu Ru is equal to G. G is the source term in this case. And we also assume that this L is invertible. So by invertible we mean that the inverse of this L exists. So just apply the invertible operator on both sides of the equations, then we will have exactly a general form like this one. So as we claim that this is invertible, so it gives you identity. This is equal to identity, or in other words, if you use the concept of group theory, so by invertible we mean that if the inverse of any operator exists, then their multiplications gives you the identity. So this further this equation reduced to exactly this form: u is equal to uh, f minus the uh, remainder term, L inverse into the remainder term of the unknown function. Now, why this L inverse G is equal to F? How it is equal to F? If, for example, if we say this G is a constant and L is invertible operator, so for instance, if you have the first order differential equation, so then this invertible operator will be one time integration of this constant if G is any constant. So once we integrate this constant term and invoke all boundary condition in this constant term, then the solution which we have in this case is a dummy function. F is a dummy solution of this uh, source term. So we are just replacing uh, uh, this integration of the source term in a dummy function, which is f in this case. So this is now the operator form of the Edomian decomposition method. Now in next step we are going to replace this individual unknown function u by a series of in a series form, which is in this case has exactly this one: u is equal to summation n from 0 to infinity un. This is called the series of the unknown function u. So we are just replacing this u by this series form, and the equations 3 in previous slides reduced to exactly this form. So this is now the series form of the uh, equation number 3. uh, and in this, if you uh, open this series form, so this series form can be written in this form as well. And this is exactly uh, the series form in which u naught, u1, u2, u3 are the unknown functions which are depending on the variable x and y. And this is again the remainder term, and L inverse is the invertible linear operator. So this u naught is equal to this dummy functions, which is the solution of the source term. So we claim that this u naught is equal to this f, and all other terms like this one, this u1, u2, u3, and so on has solution in this remainder term. So this uk plus 1, so we are, u naught is exactly the dummy function, and all the further terms is denoted by uk plus 1, where k is greater than or equal to 0, is equal to L inverse this form, this remainder term. So once we substitute k equal to 0, so it gives you u1. This will give you u1, and in uh, right side of this equation it will be u naught in this case. So once we have the solution of u naught, so we will use this solution in this remainder term, and once we integrate the solution of u naught, it will give you the result for u1, and the process is recursively increasing. So this is exactly the general form of the domain decomposition method, in which we have the zeroth order solution and all other solutions for for the unknown functions. Now, once we have the solution of all unknown functions, like u naught has this solution, if we have the solution of u1, the solution of u2, and the solution of u3, then when we sum up all these order solution in this form, then this will be exactly called the series solution of the domain decomposition method, and it will give you the result of u in a series form. So this is now exactly called the domain decomposition method, and by this method we can solve any linear as well as non-linear differential equations. So in this slide, what are exactly the essential features of a domain decomposition method? The first step is express the linear or non-linear PDEs in a operator form. If you have any ODEs or a PDE, then the first step is for a domain decomposition method is to express this that equation in a operator form, and the second step is apply the inverse operator on both side of the equations, and uh, then after that, the third step is replace the unknown function, one individual unknown function, in a series of functions in both side of the equations which you have in an operator form. So once you reduce the whole equation in a series form, then uh, find the zeroth order solution by integrating the source term of the differential equation, and definitely you will have the boundary condition for the differential equation as well. So once you substitute all the information or the boundary condition in the zeroth order solution, the zeroth order differential equations, then you will have the zeroth order solution for that differential equations. And once you find the zeroth order solution, then all other solutions can be find by using this zeroth order solution, and this is a recursive scheme or recursive process that the next term, the solution of next term is depending on the solution of previous term, and the process is going on, and we will have the solution for the nonlinear or linear order differential equation. So this is this was a bit about the Edelman decomposition method. In next slide, or in next lecture, we are going to solve some questions, some examples using the domain decomposition method. So at this stage, if you have any problem, as we discussed this method in your class as well, so if you have any problem in this slide in this lecture, so you are free, you can easily ask from me, and the queries and the questions can be solved by any channel like WhatsApp, or we can also arrange a Microsoft meeting if you have any queries. So all the queries or the questions can be solved using the Microsoft meeting. So you are free to use any channel by asking any question.